now we will start seeing some mathematics connected to the description of geometry and motion of robot manipulators. Since we have already mentioned that our robot manipulator will be a chain of rigid bodies connected by joints, we will start today with overviewing the ways in which we can describe position and orientation of a rigid body in space. And this rigid body will be a generic link of our robot manipulator, or more specifically, the end effector body carrying some tool or payload of our manipulator. But for the benefit of abstraction, now we will consider just a generic rigid body in space. So how do we characterize position and orientation? We have to make sure that we start from solid ground. So we define some reference frame in which we will describe whatever we need to describe of geometry and of motion. For instance, the reference frame A with the three axes, orthogonal axes, XA, YA, ZA. Pay attention that we will always make use of right-handed frames. By right-handed frames means that the vector product of the unit vector aligned with x and y, so x vector y, will produce the direction of the z-axis. This is a right-handed frame. And we will only work with right-handed frame. Of course, you can do the whole course with left-handed frame. What you are not entitled to do is change frame from one type to the other while doing things, okay? Otherwise, you will get messed. So in terms of this reference frame, we place somewhere this green body. And it's convenient, since it's a rigid body, then you may remember that it's not important the description of which point we are using for characterizing the position. So we will replace from now on this body with another reference frame, of course right-handed, which we call RFB, which is placed somewhere attached to the body and has its unit axis, XB, YB, and ZB, starting from this point. Okay? It's not said that the origin B of this frame is placed physically on the link itself. For instance, if I want to describe the position orientation of my forearm, I may use a frame attached here, which then moves together with this body, so change position and orientation in space. But I can also use this frame as long as this frame moves exactly in the same way. So it's attached to the body. Okay? So attached means not on the body, but moves with the body. Okay? So then if you remove the green body, it's a matter of describing the relative position and orientation of frame B with respect to frame A. So let's talk separately about position and orientation. So to characterize the position of frame B, namely of the body that we are interested into, we just characterize the position of its origin. Why not? Okay. How do we characterize this? Well, with a vector PAB, which says where is point B placed with respect to frame A. Okay. Now, the vector PA is an object, so sometimes you may be used to look at it with a vector on top, but we don't use this notation. But this is a vector. And as a vector, it can be represented in several ways, several coordinates. So the most natural one would be you have this XA, YA, ZA, and you have your vector P, in particular PAB now. So you project this on the plane, and you will have a coordinate Z, a coordinate X, and a coordinate y here. Okay? So this is Cartesian coordinates. Of course, you may use other set of coordinates. For instance, you may use cylindrical coordinates. Cylindrical coordinates. These are Cartesian coordinates of that point or of that vector, let's say vector going from the origin to that point. Okay? Cylindrical coordinates means that, well, these are defined like r theta h, and the h is exactly the height here, and then you would say that the r is the distance, and then the theta is it's like a cylinder, no? So you say, I'm rotating, I'm at that distance, r, so theta, r, and then I'm this height, h. And in fact, you can move from generic coordinate x, y, z to cylindrical coordinate in an easy way. Okay? So for instance, you can write, better say, the opposite. You can write x, y, and z. Well, the third one is easy. Z is just like the height. Okay. While this one is r cosine theta and r sine theta. So given a representation of this vector with cylindrical coordinates, so r, a triple r, h, theta, you can compute Cartesian coordinate. Can you do the reverse? Well, yes, you can. In fact, you should write r theta h as function of x, y, z. So let's start from the top, from the bottom, which is the easiest one. You just reverse this. Okay. And now, r, what is? It's the distance from the axis z. So in fact, it's just square of x plus square of y, which gives r square cosine square plus r square sine square. So the total is r square. Then you extract the roots, and you keep only the plus sign, because this is the distance, and you have r. What about theta? How can you find out theta? So somebody says arctangent of what? Well, you say arctangent means that you want to first take the tangent. So you probably make y divided by x. So r disappear, and you have sine over cosine, so tangent of theta. So this would be yx. Okay? Well, remember that the arctangent takes only values in not in the 360 degrees. Okay? Only between 0 and pi. So if my point was behind there, this function would project it to the front, which is wrong. We will see later on that there's a better function than that, which is the atan 2, which takes both arguments like before, but works on the 4 quadrant. And before doing the ratio between y and x, looks at the sine of y and the sine of x, and then decide where the computation should put the angle. And this is defined over 360 degrees. We will come back later to the property of this. Of course, this function, nor this function, is defined when x and y are 0. In fact, when x and y are 0, so we take a point which has only some component z, and we would like to compute the cylindric coordinates, then we certainly say that r is 0. We say that h is z, but then the angle theta is not defined, maybe any. Actually, there are infinite solutions. You see, this problem of mapping and inverse mapping that may be well-defined or not. For instance, this mapping is always well-defined. So in this direction, you don't have singularities. In the inverse mapping, you may have some situation where you have to take care, so you don't evaluate this function in that cases, okay? Because it makes no sense. Even if the function for one point can always be defined, you can set the value that we prefer for one point, but in general, it's better to not evaluate the function out of its domain of definition. Okay, so this is it for position. There's nothing more. The only thing that I would like you to take into account is that when you're expressing a vector, let's forget about cylindrical coordinate. Now let's use Cartesian coordinate. Even if you don't think about it, you're expressing this, the three coordinates, the three numbers, are implicitly making reference to a reference frame. So the same vector, which is a geometric object which lives in the free space, in the cloud, if you want to, can be represented with respect to different reference frames. And we need a way of changing these three numbers depending on the fact that we are using this frame or, for instance, the B frame as a reference. Okay? So we will come back on this immediately. Now, what about orientation? Well, let's cancel this. Orientation, there are many ways for representing it, and we will devote quite a lot of time to representation of orientation. But the more classical and global one, we will see what global means, is using a rotation matrix. It's strange because I would call it orientation matrix because it's used for representing orientation. But we will see together pretty soon that why it is called rotation matrix. So a rotation matrix is a 3 by 3, like it's 3 by 3 because we are living in the three-dimensional space. If we would define rotation matrix on the plane, they would be 2 by 2. If we define rotation matrix in an n-dimensional space, which we cannot measure, we cannot figure out what it is, it would be an n by n matrix. This is the powerfulness of matrices. So, which is orthogonal and normal, which means orthonormal. Do you know what an orthonormal matrix is, or an orthogonal matrix, or a normal matrix is? Well, the matrix can be represented by vectors, they're columns, and a matrix is orthogonal if the columns are orthogonal to each other. For instance, the three unit vector along x, y, and z are orthogonal. Okay? It's normal if its columns have unit norm. For instance, the unit vector of x, y, z are unit part of, if arranged in a matrix, would lead to a normal matrix. So orthogonal and normal is orthonormal. Now, an orthonormal matrix has this property, that its inverse is equal to its transpose. This is fundamental. Okay? However, rotational matrices are not only orthogonal, orthonormal, plus they have determinant equal to +1. You can have orthonormal matrix with determinant -1. Okay. For instance, this matrix is orthogonal. Yes, because the ones are spread. So when you do the scalar product of the columns are also the three vectors are units. Sure, square plus square plus square, root square of it, it's 1, 1, 1. The determinant is -1. So this is an orthonormal matrix, but it's not a rotation matrix. So it does not represent an orientation of a frame with respect to another frame of the same kind. Okay? So this is important. We will use in particular, so we will use this type of algebraic structure to represent the orientation of frame B with respect to frame A. And we will use this notation. R, let's say B A means that this matrix represents the orientation of B with respect to frame A. Here we are explicitly bringing in the dependence on the reference frame. And if we want to do the same for position vector, I forgot to say that, is a generic P vector, when we are expressing it with three numbers in Cartesian coordinate, we add an A here to say that these are the coordinates when the vector is expressed with respect to frame A. Okay? So you see that a superscript in front of this object means the frame with respect to we are doing computation. So this is the orientation, and we will see now what this means. Well, we may also have this kind of reverse operation. What does this matrix represent? It represents the orientation of frame A as seen from frame B. So exactly the inverse operation. And because this is an orthonormal matrix, this inverse operation is just a transpose. And in fact, we can write that this is equal to RAB transpose. And we can also write that if we do this product, we obtain the identity. So when we are representing the orientation of frame A with respect to a frame B, and then we're representing the orientation of frame B with respect to frame A, when we concatenate this operation, so we make the product of rotation matrix, we are in fact representing frame A with respect to frame A. And doesn't change orientation, so it's the identity. Okay? Now, you may wonder, but why identity means no change of orientation? We will see right now. But keep in mind that there are this simple algebraic relationship. So, how is this generic matrix made of? It's made of the representation in frame A of the three unit vectors which characterize the three axes of frame B. So we have xb, it's a unit vector in the direction of B. When we represent it in frame A, we have to project this vector on the three axes and take the three numbers. Okay? And same for this, and same for that. And now you can start realizing that this type of relation implies that you have unit vectors. Why? This is a unit vector, and it remains the same unit vectors if we express it in frame B or if we express it in frame A. Its norm does not change. We are just looking at this vector from different direction. Okay? Same for this and same for this. So these are all unit vector. And even orthogonality. If two vectors are orthogonal, xb and yb, they remain orthogonal if I express them in some frame or in another frame. It doesn't matter. It's invariant, that. So this is orthonormal matrix. In addition, since the reference frame is a right-handed frame, then its determinant will be +1 and not -1. Okay? So remember that these are the things. Now, if I look at a generic column here, for instance, the second one, the number that I find here, which characterize projection of a unit vector yb along xa, which is a unit vector, ya, and za. So they are scalar product of unit vectors. You remember the rule of what is the number coming out of a product of two vectors. It's norm of one vector times norm of the other vectors times the cosine of the angle between the two vectors. Since these are two unit vectors, the norm are 1, so what remains is just the cosine. So these are so-called, the numbers here are directional cosine of the axis yb with respect to xa, ya, and za. And same for the other two columns. So, if we want to write it more explicitly, here, you see that I'm taking the three unit vectors xa, ya, and za, and I'm projecting them along xb, restart. I'm taking the unit vector xb and I'm projecting it along xa, ya, and za. So I'm doing the scalar product of xb and xa. So xa transpose is a row times xb a column. Both are unit vectors. So what is there? The cosine of the angle in between. And same for the second component, same for the third component. So this is what I compactly rewrite as xb expressed in frame A. So the first column of the previous slide. So it's xb expressed in frame A are these three numbers. Same for the second column. This is the unit vector yb expressed in frame A, which means that I project and do the scalar product of yb with the unit vector of x of the frame A, and then with unit vector y of frame A, and then of unit vector z of frame A. And same for the last one. Okay. The result is an orthonormal matrix with determinant +1. And this is one, for instance, just to remind that. Now, there is another important thing which is implicit in this relationship. So there's a chain rule property, meaning that if I take a generic rotation matrix, again, which represent the orientation of a frame with respect to another frame, and I multiply for another rotation matrix, the product is again a rotation matrix. So again, it's orthonormal with determinant +1. Okay? So we have, in fact, the structure of a group, and this group is called special orthogonal group of dimension 3. Dimension 3 is because these are matrices 3 by 3. So you have in general special orthogonal group of dimension n. It's orthogonal because this is made by orthonormal matrices, and it's special because it has the determinant +1. Okay? Now, it's a group, so if you concatenate element with the product operation, you obtain another element of the group. So you obtain again a rotation matrix. And as every group, it has a neutral element, So if you multiply a rotation matrix by the neutral element, the rotation matrix should not change. What is this element? Is the identity. Okay? And finally, the inverse element also should exist in a group, and this is given by the transpose of the original element. Okay? Because these are orthonormal matrices. Now, there is a nice interpretation if you do things properly, like we did it here. So if you have this inner index, so the subscript of the first matrix and the superscript of the second matrix of the same kind, then you have a clear interpretation of what you're doing. Namely, this represents the orientation of a frame I with respect to frame K. This represents the orientation of another frame J with respect to frame I. When I do the product, I can eliminate this, and the result is another matrix, which is again a rotation matrix, which represents the orientation of the last frame J with respect to the original frame K. Okay? Well, you may wonder, what if I exchange the order of this? So what if I'm taking these rotation matrices and I'm writing instead Rej times Rki. What is this? So first of all, is it Rkj? No, why not? Because in general, the product of matrix is not commutative. Okay? These are rotation matrix, special matrix, no wonder. I said in general, and in fact, because of their interpretation, if this rotation matrix represents change of orientation, both with respect to the same axis, then they commute. Because if I'm rotating around some axis by some angle, and then I'm rotating again by another angle, and if I interchange this angle, I obtain the same final orientation. Okay? So the product in that case would be commutative, but in general it is not. So this is not. So what it is? The inverse the identity matrix? Not really. I would say nothing. It's a rotation matrix. It's a rotation matrix. It's a concatenation of two rotation matrices. Represent an orientation, because the result, because of the structure of a group, is again a rotation matrix. So again, it represents some orientation. But it's just, I've made some change of orientation, and I'm in the first one, then another change, and this is the final result. But what it is, I don't know. Okay? So, let's do, okay, maybe I have, so this is the note that it's important. Let's do some example, a very simple example. Now, I used to do this with a Coke can, but this would be too commercial, so I'm using an Italian product. Okay. Suppose that you have this bottle. Wow. Okay. With this brand on it. And suppose that we have this bottle with the name in front and oriented like this. Okay? So its main axis is along ZA, and the center of the name is on XA. And now suppose that we define, I have here an example, we define some orientation with this matrix RB with respect to A, and the matrix is simple, this one, 0, 0, minus 1, minus 1, 0, 0, and then, of course, 0, 1, 0. Okay. Now, if I'm bringing the bottle which is in its neutral orientation, and I'm assuming the orientation of frame B, how would the bottle be placed? I drink in the tea. Well, easy. Remember, what are these columns? What is this column? First column of this rotation matrix represent what? Represent the directional cosines of x of axis xb when I'm projecting it along xa, ya, and za, which means that the 0 here means that xb is orthogonal to xa. The 0 here means that xb is orthogonal to ya, and the minus 1 here means that xb is aligned with xa but has the opposite. Okay, so this is the origin of A, which coincide with this origin, but now for clarity I'm drawing this. So the first axis, xb, this is xb with respect to A, is oriented like minus za. So it's oriented like this. Okay? Now, what is this? This is yb expressed with respect to A. So I have to draw the axis yb, where it is oriented. Is the opposite side of which axis? Of xa. So xa is here, and it's coming, so this is, now in perspective, it's going. So yb is here. And what is this? Is zb expressed with respect to A. So when I project it, it's orthogonal to xa, it's orthogonal to za, it's giving just the direction of yi. So it's poof, poof. It's oriented like this. So this is zb. First question, is this a right-handed frame? I don't know if you see it. Huh? Yes, because it's difficult to make it. Okay, but x, then y goes inside. So if I'm looking from here, I see x and y in the correct way. So this is a right-handed frame. And this result is just because this has determinant plus 1. If I'm changing a sign here, if I put minus 1 here, I would have obtained the same x and y axis of frame B, but this would be reversed, and this would be a left-handed frame. So I'm going from a right-handed to a left-handed. And then if I mix product like this, I'm losing my mind. Okay? So this is correct. So result, how is the bottle placed? Oriented, I would say. Well, it has also, it's always in this main direction. Okay. And where is the name? Not really. Huh? It's at the bottom. So it has moved from here to here. And then so. Okay? So you see that if I give you a generic rotation matrix with numbers, you can always understand what is the frame behind this rotation matrix if I give you the reference frame. So if I give you the frame with respect to which I'm expressing things. Otherwise, it's not really. Okay? So the rotation matrix, again, is an object. It's an abstraction. Does not need to carry subscript and superscript. Okay? Because it's an orthonormal matrix with determinant +1. It's one generic element of this special orthogonal group 3. So I don't care. I can make computation with that. But if we are using it as a representation of orientation, then I can interpret the columns as orientation of the axis of one frame with respect to the other frame. And this solves our problem of representing things. We will see later on that this representation is somewhat redundant, because we have 9 numbers in this 3 by 3 matrix, although these numbers cannot be arbitrarily, because they should be such that the columns are orthogonal, such that the columns are unitary, and such that the determinant is +1. Okay, so there is no more compact representation like the one that we suggested at the beginning. In order to represent the orientation of this body in space, I may need only 3 angles. So how is this related to these 3 by 3 matrices? We will see how to make this transformation, and the fact that we can make more compact the representation of orientation, so not using rotational matrix but just 3 angles, but we will run always, no matter how we do this, into singularities. So there will be some representation, some orientation that cannot be represented in a compact way, given this minimal representation. But rotation matrix represent all possible orientation. So in this sense, they are global. Okay. Now, let's see another aspect. Now, let's go back to position vectors. And now we have this vector from origin to P, or just P. We forget about the origin. So it's a vector P. So when we say a point, we implicitly think of a vector going from the origins of the frame to that point. And expressed in frame 0, so this with axis x0, y0, zeta 0, it is given by 3 numbers, which we call px0, py0, pz0. Okay? For instance, if this vector was aligned with y, its number would be 0, some value which is the length of this vector, and then 0 again. Now its generic position is like this. Now when you're writing it in this way, you should think that you're representing the same generic structure of a vector with numbers, because you're expressing it with reference to some reference frame. So in fact, I can rewrite this 3 number in a more complicated way. I can say that the first scalar is the weight of what? Of an axis x1 expressed in sorry. No, I'm going ahead. Okay, before doing this, there's one step in between. Okay, I can write this P0, so Px, Py, Pz, 0, 0, 0. And then I can rewrite this as P0x with respect to a frame, an axis which is made like this, and then Py0 with respect y0, 0, and then Pz0 with respect to 0, 0 axis. Okay, this is missing. So what I mean by that? I mean that these 3 numbers are organized in multiplication of 3 vectors. This is the x0 axis expressed in frame 0. So this is simply 1, 0, 0. Okay? This is same thing, it's the y0 axis expressed in frame 0, so it's 0, 1, 0. And same here. Okay? So you're actually organizing things. It's like rewriting this by identity matrix times the same original vector. You see, when you do the product of the identity times this, you have first column times the first scalar, second column times the second scalar, third column times the third scalar. So what you're actually saying is that you're not changing your reference frame. You're giving a reference frame. You have 3 numbers in the same frame. It's like using the identity as the transformation. You have not changed the orientation. Now, suppose that you want to represent this in a different frame. In a different frame, and the different frame is frame 1. So you take the same vector, and you're now, instead of reading this 3 number in black, you would like to read the 3 numbers which are the projection of this vector along the unit axis of the frame 1, the rotated frame, in a sense. So what you need to do is to obtain some representation of the orientation of frame 1 with respect to frame 0. So you're writing R01, which is characterized by the unit vector x1 projected on frame 0, unit vector of y projected on 0, and so on. And then the 3 number that will result from this identity will be the coordinate of the same vector, so px, py, pc, now expressed in frame 1. Okay? Or that expression on top. So what you're doing is you're having a way of changing coordinate of a vector. In particular, if you know the vector expressed in frame 1, so you know these 3 numbers, in order to compute its expression in frame 0, so these 3 numbers, you have to build the rotation matrix of frame 1 with respect to frame 0. Okay? And vice versa. If you know these 3 numbers and you would like to know the expression of the same vector in frame 1, you have to isolate P1. How do you do this? By pre-multiplying by the inverse of R01. So you have P1 isolated here, and you will have R01 transpose P0, because the inverse is the transpose of this matrix. So let's do one example of application of this. And pay attention, this is very important in robotics, because sometimes you know some information about an object, a point, expressed in the reference frame of a sensor. For instance, you have a touch sensor or a force torque sensor on the wrist, and you're measuring a force in that direction. But in fact, you would like to know this force, how it is expressed into the reference frame of your lab or your table or your cell, whatever it is. Okay? So you need to do this change of representation. So for instance here, suppose that you know a vector in frame 1, and this vector is just P1 is 1, 1, 1. Okay? So if I want to represent this x1, y1, z1, this would be a vector which comes out like this and is along the, okay, and its length would be square of 3. Okay, so it's in the principal orthogonal sector made by positive value of x, y, and z and pointing there. Now, suppose that I would like to know P0, so these numbers, when I know that this frame, with respect to the 0 frame, which may be my reference frame as all, is characterized by this matrix. Okay, strange enough. So first of all, if this is our problem, somebody says, okay, this frame, which is the sensor frame in which you measure this vector, which may be a force, which may be a velocity, whatever it is, I know that you're reading these 3 numbers, but in fact I want to know the expression of the same vector in the frame 0, which is characterized by this. First thing, you don't believe that. You check that this is a rotation matrix, because otherwise your computation makes no sense. Okay, is this a rotation matrix? Well, let's check at the normality. This is square of this is 1 over 3 plus square of this 1 over 6 plus square of this 1 over 2. So it's 2 over 6 plus 1 over 6 plus 3 over 6. So it's 6 over 6 is 1. Okay? Same thing like this, because when you square the minus sign here, it doesn't matter. And here, same, 1/3. It's correct, no? Yes. No. In fact, it's not correct. There's a 2 missing. Okay? So don't believe it. Check it first. Are they orthogonal? Well, I should make the product of this times this. So this gives 1/3. This gives 1/6. So 1/3 plus 1/6 minus 1/2. And this is 0. And then of this times this, and of this times this, and if I haven't, yeah, okay. They should all be 0. The last thing you should check is that the determinant is +1. So, but let's take this for granted. No? But don't forget to verify this. Now I make the simple computation. P0 is R01 P1. R01 is here, P1 is here. So when I do this product, I should sum the columns. No? So here, first row is this plus this plus this. No? So it's 3 over square root of 3, which is also square root of 3. And this is the first component. Then I should sum this one. So second row times this column, this plus this plus this. So it's 1, 1 minus 2 all over square root of 6. So this is 0. And finally, I sum the 3 columns because it's 1, 1, 1. And this gives again 0. So this vector is just this one and has only one component in that direction. So I should compute how are the y and zeta 0 and z0 axis of frame 0, but I can certainly say where is the x0 axis. Do you agree? If I now need to draw here, where is frame 0? Well, I can say that this axis is the x0 axis. Why is that? Because the same vector, the vector didn't change. No? But I know that its expression in this frame has only the x0 component, so it lies on the x0 axis. And then there will be some, say, y0, z0. I don't care now. Okay? So remember, the vector has not changed, just its representation. So the numbers that we use for carrying over computation. The vector is always the same. Okay? So, outcome of this is that the same object, the rotation matrix, that we have introduced for representing the orientation of a frame with respect to another one, is also used for changing coordinates of a vector when expressed from a rotated frame with respect to a fixed frame and vice versa. Okay? It's exactly the same object. Now let's do a last step, which is the following one. Suppose that we do a rotation. We are doing a rotation of a fixed frame. And here, to make things simple and computable easily, we do what is called an elementary rotation. So we start from a reference frame. Suppose that in this case I would take x, y, and z, so like the walls of this room. And now I'm making a rotation. And I end with a frame which is rotated, and I call it RFC. So the z-axis did not change. Okay, so I've made an elementary rotation around one of the main axes of the original frame, in particular, in this case, around the z-axis. Now, if I look at a generic vector, and since I'm doing computation in the plane, I will put this vector on the plane, or imagine that this plane is not the z equals 0 plane, it's just some z plane, whatever. Okay? And suppose that of this vector that goes from the common origin, you see that there's a common origin here, to that point P, I know its coordinate in the rotated frame. So I know what is called here U, V, and W. W would be the z-axis. Okay. Now what are the, so I know these numbers, U, V, and then whatever is z, and I want to compute the black numbers x, y, and z. Well, let's take z out of the plane in the sense that it's the same. We just made a rotation, so whatever was its height of this point, it's remained the same. So z is equal to w. But what about the other? Well, the other needs some trigonometry. Very simple. So this x is computed like OB minus XB. But OB is just U, and there's a theta angle by which I have rotated the frame, and this is cosine of theta. And then I have to subtract this, but due to geometry, I know that that angle over is exactly theta, and so this part is just the sine of theta by the arc, which is nothing else than V. Okay? Similarly, in order to evaluate y, I sum OC, which is just u times sine of theta, and then cy, and cy, I look at this angle again, and I have the radius, which is v, and then now multiplied by cosine of this theta. So I have this expression. And this holds no matter if I've rotated by theta positive or negative, it's generic expression. But let's organize them in a smarter way. And then I see that if I take the components of this vector in frame C, so what I would have called 0p or just p expressed in C, so the three number u, v, w, looking at this, I can multiply it by this matrix and obtain what is on the left, x, y, z, which is nothing else than the coordinate of p when expressed in frame 0. So this is a rotation matrix. And since it's an elementary rotation matrix, because I've rotated things around the z-axis, I call it in this particular way with the z, okay, by an angle theta. You can immediately tell that this is an orthonormal matrix. Now it's easy because this cosine sine square, 1, orthogonal cosine minus, sine cosine plus, these are on the 0, so, and then the determinant cosine square plus sine square times 1, so it's 1 plus 1. And again, what is the axis, z-axis of frame, of the C frame? Well, it coincides with the z-axis of the 0 frame, 0, 0, 1. And again, these are directional cosine of the x-axis of the C frame, the rotated one, and the y-axis of the C frame, the rotated one, when expressed to the original. Okay? So now we have given a structure to this rotation matrix to represent in the change of coordinates. We are using the idea of change of coordinate, but we know that to change coordinate we need a rotation matrix, and so this rotation matrix represents also the orientation of frame C with respect to frame 0, and this is an elementary, by an elementary change of orientation around the z-axis. And similarly, you can also note two things, very important, which are hold in general, that if you suppose that you're not changing by theta but by minus theta, so the frame RFC would be below probably, then you would obtain exactly the same matrix transpose, which is the inverse, which can be interpreted as follows. So if I'm rotating frame 0 by theta to frame chi, then I need to rotate frame C by minus theta to get back to frame 0. It's just the reverse operation. And the reverse is the transpose, which in this case, in the elementary case, is just changing the sign of the angle. I leave it as an exercise to obtain the elementary rotation matrix when you're rotating the frame by an angle theta or psi or whatever you want to call around the x-axis, and you have the 1 here and the same structure here as this one, or around the y-axis, and then you have the 1 on the diagonal in the second position. But pay attention here, the sign of the sinus is on the other side, on the lower triangular part of the structure. Okay? So you can do this by elementary trigonometry like we did before. So, last thing that I want to show is that the same matrix, and here is why it is called rotation, is used to rotate vector. Now pay attention, we are not changing expression of a vector expressed in one frame or the other. We are not representing orientation of a frame with respect to that. We have just one frame. But what we do is we apply a rotation to all vectors in this frame. For instance, vector v rotates and goes to vector v prime. This operation is something that in graphic card can be done on hardware on 10,000s of vector at the same time, when you're changing representation of a view, you're changing orientation, then all the vectors pointing to the vertex of, I don't know, whatever solids are in your view should change accordingly at the same time. And the power of a graphic card is that it can implement on hardware this operation of a huge amount of data. Okay? So this is one thing. You see that I have only one frame here. No other frame to represent, no change of coordinates. Just I have a vector, and now I'm rotating the vector going there. How can I represent the coordinates of this vector after this operation of rotation? Not wonder. Using a rotation matrix. And this is why it's called rotation. Okay? Let's do things simple and make this rotation as an elementary one, so around the z-axis. So I have a vector there on the plane xy or on any other plane at the level z, and I'm rotating this vector by some amount, let's say theta. So originally the vector had an angle alpha with respect to the x-axis and had coordinate x and y, which can be expressed in this way. No? So the modulus of the vector, v bar, and then cosine and sine of alpha. Now I'm giving this rotation by an angle theta, and I obtain v prime, which has coordinate x prime, y prime, and z prime. Z prime has not changed, so forget about this part. And now I can do some computation, because the new angle is alpha plus theta. Now, the original one plus the one of the rotation. So I can represent the coordinate x prime, y prime as before with the right angle. So modulus of v, cosine of alpha plus theta, and sine of alpha plus theta. Now I expand this trigonometric sum, and I have cosine cosine minus sine sine, and sine cosine plus cosine sine. And then I recognize, for instance, that v sine alpha is just y multiplied by cosine theta, and v cosine alpha is just x multiplied by sin theta, and I have this expression, and similarly as above. If I reorganize things in a matrix way, no surprise, I have found, as before, that the coordinates of the rotated vector with respect to the original coordinate are just obtained by the elementary rotation matrix around the z-axis. In fact, I was giving a rotation around the z-axis. But this holds true if I'm giving a rotation around any axis to any vector, and the results of the rotated vector is obtained through the rotation matrix applied to the original coordinates. And again, rotation. This is why it's called the rotation matrix. So if we summarize these things, we have three equivalent interpretations of the same mathematical object. This orthonormal matrix with determinant plus 1, which is a rotation matrix, can be used as such for doing three things. First, representing the orientation of a body or of a frame with respect to another frame, the first things that we have introduced. Second, to change the coordinates of some vector from one rotated frame to an original frame. Finally, as an operator which rotates vector, the third interpretation that we have just seen. So all of them are represented by rotation matrices. The name rotation remains even if we are using it for representing orientation, or if we are using it for changing coordinates of a vector. Okay, now short break, which is of the computational nature. Suppose that now we have several reference frames, and it's not by chance that I'm using this example, because this is exactly what will happen in the direct kinematic of a manipulator. I'm starting with a frame attached to the base, then I attach a frame to each link, and then I have to describe position and orientation of one link with respect to the previous one, or of the associated frame with respect to the previous one, and then of the following one with respect to the previous one, and chaining things and doing product, I will obtain the final orientation. Okay? There is also the position and the displacement to take into account. We will see this later, how to do both things together. Now just orientation. So in this slide, I have a reference frame here. Then I have placed another reference frame here just for the purpose of clarity. In fact, the origins are coincident. Okay, just not to draw several frames in the same place. So this displacement, which is locating the origins of frame 1 with respect to frame 0, in fact is 0, so it's not there. Then I have another frame, RF2, again with same origin, but I've displaced it just for the sake of clarity. And then another one, again placed like this. So I have 4 frames, RF0, 1, 2, and 3. Pay attention. 4 frames, although I'm ending with 3, because we start always with the 0 frame. Okay? So there are 4 frames, all with the same origin, but each of them has a different orientation. So I'm using 3 rotation matrices to represent their relative orientation. So I'm using matrix R01 to characterize the orientation of frame 1 with respect to frame 0. Matrix R12 to characterize the orientation of frame 2 with respect to frame 1. And finally, R23 to characterize the orientation of frame 3 with respect to frame 2. And now I have this problem. At the end of this chain of frames, I have a vector, and I know the coordinate of this vector in that frame. And I would like to compute its coordinate into the basic frame. For instance, to understand if that is a velocity, and I'm reading this velocity on board of the last frame, I want to know if this velocity with respect to my reference frame in this room, it's in that direction or in that direction or whatever. This is the reason why. I'm on board. I have a sensor, like a mechatronic device on the space shuttle. No? I have a camera looking between the gripper, and I don't know how this camera is placed, so I don't know where is this object going with respect to the reference frame. So I need to do this transformation. So how do I do this? Well, I apply the chain rule. I express this into several times by multiplying rotation matrices, and I obtain the result. But this can be done in 2 different ways. One is the following. So I'm building up by multiplying the first rotation matrix times the second and times the third. Now it's the chain rule repeated. So this product expresses what? The orientation of frame 2 with respect to frame 0. And then this product as a whole can be written in this way because the simplification of contiguous subscript and superscript are consistent. So this cancels this cancels this. So what is left is representation of orientation of frame 3 with respect to frame 0. Fine. Now I have this vector. I multiply this vector by this matrix, and I'm done. Okay? There's another way of doing things, which is the following one. Now, well, I take this vector. I know it's the 3 numbers. And first, I express it in frame 2, which means that I do the multiplication of R23 times P3. What do I obtain? The representation of the same vector in frame 2. So what I would call P2. And now I apply the second rotation matrix, and I express the same vector in frame 1. And finally, I apply the first rotation matrix, and I express things in P0. Very simple. Now, which is better? This includes 60t product and 42 summation. This only 27 products and 18 summation. Very simple problem where the issue of computation and how fast we can do this. Now products and summation can be done very fast. So it's just a matter of theoretical point of view, which shows that having an expression of things, it's not enough in robotics, but the way in which you organize computation is important because you have to do this computation several times in real time with changing data. So you cannot neglect the issue of computational complexity. Now, of course, I would say this is better than that, unless the same operation should be applied not just to this vector, but to a multitude of vectors that I know at the same time in frame 3. If I have 100 vectors known at some instant of time in frame 3, then it's much better to compute first the rotation matrix once for all, R03, and then apply it to the whole bunch of vectors. It's clear the safest, the optimal things. Okay, so there's a trade-off. Just for one, it's okay. I think that for 2 are on the borderline. For 3 or more, it would be definitely better to organize it first, this rotation matrix, and then apply to the multitude of vectors that you need to transform. Okay? So depending on the task, one method may be convenient with respect to another one. Okay, I think that we won't have time to go through all of this now, but let me introduce the point and introduce some mathematics. We will do now, in the last 15 minutes, mathematics on the blackboard. But why do we need this mathematics? First of all, now we want to represent, now that we know that rotation matrices are very nice, we can do several things. Now we want to solve this problem. Suppose that I have a vector, and I want to see what is its representation after a generic rotation. Not an elementary one around x-axis, but around a generic axis, which I called R, and by a generic value of angle theta. So I'm saying I have this vector, and I have this vector R, and I want to do a rotation of some angle theta around this axis. So how do I represent this rotation? Knowing only few numbers, the directional cosine of this unit axis, so 3 numbers, but actually only 2 because the third number should make unitary this vector. Okay? And then the scalar theta, which is the angle around which I'm rotating. If I do proper computation, I will obtain a rotation matrix which is a function only of small r, so the vector r, and the angle theta. And this is the so-called direct problem. So I find a rotation matrix parameterized by the axis around which I'm rotating and the angle theta, such that this matrix will rotate whatever vector I'm considering. Because, of course, I'm rotating the world around this axis by an angle theta. So whatever vector then will leave will be rotated by this. The inverse problem will be, okay, I have this rotation matrix, numbers, orthonormal with determinant +1, but numbers like this one. Then I say, okay, but this, if I forget that this is 0, 1, it's a generic rotation matrix. Can I represent this rotation matrix as an elementary rotation of an angle theta around some axis r? And this is the so-called inverse problem. So given a rotation matrix, numbers, I want to find the so-called invariant axis of the associated rotation and the angle rotating around this. And we will see that the direct problem is relatively simple. So build up a rotation matrix only with those data. The inverse problem is already one of complexity similar to those complexity that we find in solving the inverse kinematic of robot manipulators. So for instance, it may not have a solution, or it may have, in general, has more than one solution. Before doing this, and we leave the rest of the slide to the next lecture, I would like to recall a bit of mathematics, and in particular, algebra of vectors. I have here listed things. Okay, first of all, let's do this simple example. Suppose that this is vector r, and here I'm standing with my head on the arrow of the vector r. Okay? So now the world is rotating around me by an angle theta. So I will have something like that. And in particular, if this is, I call this axis x or whatever, I will go to x prime by an angle theta. Remember that we compute positive angles when we rotate counterclockwise around an axis. So when I'm standing like the axis of rotation, I see the axis rotating like the opposite of our clock. Okay? So this would be a positive value of theta. And same, if I'm going from here to there, and this is rotation theta. For instance, this may be 30 degrees. Okay? Now, suppose that the rotation is like this. And so it goes like this. What should I write here? What is that angle? Minus theta. Okay, good suggestion, because this is wrong. Okay? This is, again, theta. But if I put a number, this will be approximately minus 30 degrees. So I'm mentioning this because of a long story of teaching robotics to students. They immediately get lost because they say, okay, this is positive, this is negative, so this is minus theta. No, it's always theta, because it's defined from one axis to the other. From one axis to the other is always theta. Then it can be positive if the rotation is counterclockwise, or negative if the rotation is clockwise. Okay? So don't make this mistake. Although the results apparently is the same, but this is defined as theta and its value is negative. This is defined as theta and its value is positive. Okay? So, now, with these premises, I have few computation to be done. So let's start with this. Suppose that you have two vectors, n and s, and they are unit vectors. It's not really important, or maybe it's, well, it's important, but it is general. So they will be defined by nx, ny, and z. I'm writing it in row, and sx, sy, sz. Now, how do I compute n vector s? Well, this will give me some vector r. And if these are unit vectors and they are orthogonal, and I take this n as x, then s as y, I will find the r vector as the z vector according to the right-hand rule. But in general, these may not be orthogonal and not be the elementary axis. Do you know how to do this? There's an easy trick, which I think it goes under the Sarrus rule. And you do the following. You organize the two vectors as rows of a matrix. And then you put ejk, which characterize the unit direction of the axis xyz of the component. And then you compute the determinant. So if you compute the determinant of this, you will find, and you expand along the, you compute the determinant by expanding the element of the last row. So you will have plus minus plus, so I times this block, so it's ny sz minus nz sy, and then plus minus plus minus, so I put a plus j, but I remember that I have to reverse things in this determinant, so I will make this product first, sx n z minus nx s z, and then again plus without changes k, and I have to, this minor here, and x sy minus sx and y. And these are simply rx, ry, and rz of the vector r. So this is the rule for making vector product, not scalar product between two vectors. No? Scalar products are so-called inner products of vectors. So one vector, I project them one on the other. So I have norm times norms times the cosine of the angle. So it's a scalar. Here, it's another vector, which has this component. Now, this can also, I will sometimes not use this notation. I will use this notation, and I'm writing that S vector, n vector S, it's also written as a skew-symmetric matrix which contains the element of n times the vector S, where the skew-symmetric matrix is made as follows. 0 on the diagonal, and then the elements minus and z and y and x with a minus, and then being skew symmetric, the other elements are exactly the opposite of this, so nz and x and minus and y. And this is a skew symmetric matrix times Sx, Sy, Sz. So what is this operation? I have replaced an operation between vectors, the vector product of two vectors, by an operation which is a product of a matrix times a vector. So I'm using a matrix which is convenient because matrix can be concatenated in an easy way. For instance, we'll see later on that this has... Now, if you do this, magically, you obtain exactly this result. So you obtain the same R. So every time we have a product of a vectors times another vector, we can replace it by a product of a matrix, which with the element of the first vector, times the other vector. So this is a skew-symmetric matrix. Do you know what is a symmetric matrix? It's a matrix where the element Aij is equal to the element Aji. A skew-symmetric matrix is a matrix where the element Aij, so row I column j, is equal to minus the element exchanging rows and columns. And here is the fact. Okay? As a consequence, the element on the diagonal of a skew-symmetric matrix are always 0, because they have to be equal to their opposite. And the only situation is that if you have a 0. So this is a skew-symmetric matrix. Now there are other things that can be said. For instance, some algebra of this. So if I have S vector n, I know that this gives minus r. So I flipping the order, so I'm obtaining the opposite direction. So which means that this is S of S times n, but it should give also S of minus n vector S. It gives us exactly the same result. So you have operation moving around things that follows from the same properties of a vector product. Another thing that we won't use now, but it's important for later uses, is the following. So suppose that you have a generic matrix A. Is this matrix symmetric or not? We don't know. It's a generic. It's not symmetric in general. And it's not even skew-symmetric. It's a matrix whatever. Well, we can rewrite this matrix as follows. We can sum and subtract the transpose and divide by 2. Okay? The result is A, because it's A half plus A half plus A transpose minus A transpose A. So any matrix can be written as these two components. Now look at these components. This one is symmetric. Okay? It's symmetric because if I take the transpose of this matrix, I obtain A transpose plus A divided by 2, which is exactly the same. Okay? This is skew-symmetric. Because if I take the transpose of this, I obtain exactly the opposite matrix. Like here, if I take the transpose and I am changing element, I obtain the same matrix with a minus sign in front. Okay? Now, if you take a generic matrix A and you put it into a quadratic form like this, have you ever seen this quadratic form? So this is a quadratic function of x written with a matrix A in between. Then if I call this A sim and I call this A skew, I can write this in two parts. Okay? Replace A with A sim plus A skew, then I distribute the product, so I have these two terms. But the skew-symmetric matrix, when put into a quadratic form, gives 0. Try with this, multiply this by that. And in fact, it's a result of the vector product also. If you take the vector product of A vector product, well, I leave it to you. Which means that every time we have a quadratic form, it is nonsense to consider a non-symmetric matrix. Just consider a symmetric matrix, because if A is generic, it can be always replaced by its symmetric part. Okay? Last concept is that if you have a symmetric matrix, do you know how are the eigenvalue of this matrix? Do you know what are eigenvalue of a matrix? I hope you do. So eigenvalues of a matrix of real numbers are in general complex number, And if you have a complex eigenvalue, you have also its conjugate pair. Okay, they come in conjugate pair. Now, if the matrix is symmetric, all the eigenvalues are real. This is a strong property. If the matrix is positive definite, which means that, and at this point I can only talk about symmetric matrix, which means that this is greater than equal to 0 and is equal to 0 if and only if x is 0. So only if you're taking a 0 vector, this is 0, otherwise this is always positive. This is a positive definite matrix. And being symmetric has all real eigenvalue, and this real eigenvalue are all positive. Okay? Similarly, if you have a negative definite matrix, symmetric, all eigenvalues are real and all are negative. Okay, so these properties will be used. This last one much later in the course, but this one with skew symmetric matrix will be used here to solve the problem. Okay, we stop here and have a nice weekend.